Okay.
Okay, so the status is I know how to solve the equal k or equal q constraints. And you can always reduce it to single moments.
Sorry, fixed K or fixed Q, right?
Yeah. So if you do 2D, say on a continuous bounded or something simple, then
so how do you, sorry, in this case, how do you deal with the spin dependence?
So for now I'm just talking about both like two generic continuous bounded things. So I'm not doing the physical.
Okay, problem. So this is not about the physical problem. Okay.
Yeah, you can do the physical problem in the same way, but it's just part of the problem.
Yeah, because I really, yeah, as I mentioned, yeah, it's really better. Yeah, it's better to. Okay, anyway, yeah, I mean, I don't think it's part of the problem in the sense that, you know, until we have a clear path about what is the reduction from the physical problem to the simplified version.
Yeah. The equal K and equal Q stuff works in the same way for spin. You can always reduce those to single moment problems.
So right, but are you sorry? When you're saying this about the single moment part, you're talking about a non-exponential spin. You're talking about a non-exponential thing, right? What are you doing? Are you doing the or?
No, you can do, because you can reduce it to single moment. Then you can use the exponential thing, and for the spin part, you know the polytope. So there's, you know, the exact constraints for the spin part. So for the continuous single moment, you'll have the exponential. For the single
recording in progress.
For the single spin, you have the polytope.
Sorry.
This is equal K or equal Q.
Sorry, so let me just what is, so how far, what, I mean, why, I mean, what is the distinction between what you're talking about now and the physical problem?
There's no distinction. So the thing missing is when you have non-equal column known row, basically. So something like the Shor's inequality. That thing I don't know yet how to get.
Okay, so it's the double moment. So whenever it's reduced to single, okay, so the status is that whenever it's reduced to single moment, and then we know what the constraints are for the single moment. Whenever the problem is either either,
yeah.
And when you have the fixed K, then you basically can implement the crossing symmetry on the fixed K, right?
Yeah.
Right. Okay. So there's already non-trivial things one can.
Yeah. So in principle, you can do, if you want to bound, say G40, we have everything we need, but I think this one is either trivial or is not bounded. I think it's just trivial or something. So it's not that interesting. You want something like G20 or G30 to bound. So right. Then the different K level.
Sorry, you're saying that so for fixed K, sorry, so what are you saying? You're saying that for, okay, so for fixed K, what can you bound? Let me ask it this way.
For fixed K, well,
what are you bounding for fixed K?
G40, because the null constraint is G42 related to G41.
So are you talking about you're bounding both G40 as well as G41?
Yeah, I guess you can bound G41 as well. So I didn't look very closely exactly what can happen, because that's, I mean, that wouldn't be so interesting.
Why?
Well, I think so. Let's see. If you go Simon's way, basically,
forget about Simon's way. I'm just saying that you're already telling us that you have so you're already telling us you have the constraint for fixed K and for fixed Q. So I'm asking, what does this constraint look like in terms of in terms of this projection on the crossing plane?
You get, well, I mean, in the simplest case, you get some bound on G41.
So you don't know what the constraint looks like on the crossing plane, is what you're saying.
It's easy to check. I mean, it's just trivial to check, basically. That's what I'm
Okay.
saying. I mean, you know, the polytope, there are just some lines, and then you just intersect with another line and you find what the intersection is. That's it.
So this is a 2-dimension thing, or is it a 3-dimension thing?
Well, it's fixed K, so it's technically like a single moment.
No. What I mean is the crossing plane is 2-dimension, right? There's G40 and then there's G41.
Oh, okay, sorry, that's what I'm confused. So I only know what the polytope is for G41, G42 space. I didn't check what it is when to include G40, but I suppose it's still some polytope.
Okay, so it's not a
I think
an interesting problem. I just want to see, you know, you have the constraint of, you're telling me that you have the constraints at fixed K, right? So
Yeah.
that means you know how to write down constraints for G40, G41, and G42.
Yeah.
And therefore you know that there's I mean, I know that there's Simone has done something, but I don't think we should be overly constrained by what Simone has done. That's what I mean, eventually we can see how it connects, but within our context, there should be something that we should understand what we're doing. Right. So okay. So the zeroth order question is just what exactly does the space look like in G40 and that crossing point?
Mhm. Yeah, I can figure that out quickly. It's not, yeah.
Okay.
But so I think even for the non-equal K, non-equal Q stuff,
Sorry. So for the fixed Q, then what are we doing?
for the fixed Q, I think the only way to do it is you do spin truncation, and then you have the geometry as a function of your spin truncation, and then you can move
So
the
why
spin.
why do you need the spin truncation?
Because there's no going around it. I mean, because
No, I know, but what do you need? Why do you need to truncate it? I mean, I'm just saying that. I mean, are you using the? Is it because you're using the non-exponential map to do this?
well, I'm just looking at, so I can check exactly what the geometry is by doing numerics, right? And then you can describe the geometry given a fixed spin truncation. Of course, you can take that to infinity, but then it's more helpful to have the spin truncation in case you need it.
Okay, but that's a statement about about your how you're doing your numerics. That's not a statement about the bound.
Yeah, it's sort of, yeah, it's, well, I don't know how to get any sort of bounds yet. Once I look at different K, unless I do spin truncation, basically, that's the problem.
When you're looking at different K.
Yeah, because, sorry, let me think. Yeah, I guess at the moment, I don't know how to formulate any sort of constraints at different K without referring to a spin truncation. But of course, this doesn't mean there's no way to do it. But yeah, I don't know.
Okay.
Because I can't do numerics and I can't do like.
Okay, can you give us a summary of what you've done so far? Maybe like use iPad or something, because I think it'll be helpful, because just speaking is yeah.
Can you do screen sharing?
Oh, sorry. Yes.
So I remember there's a 2D exponential transform for 2D moment. So that's for continuous, or?
Yeah, that's for continuous, and I also worry it's actually for, even more specifically, it works on a disk. And it,
Well, I
So-
mean, we shouldn't jump to any conclusion yet until we actually figure out what it actually does. Because, I mean, we don't know what it, we don't know what the constraint is actually. Because we haven't figured out what the kernel is. And it's just, you have an exponential, you have a double exponential map, but then you also have a kernel that is associated with it in order to define the constraint. I find it unlikely that it's, so my personal view is that I find it unlikely that it is only for particular things because of the fact that the 1D exponential thing is doable for anything. And then and since it's also similar, and in 1D you also know why it's, you also know exactly why it can be done for any kind of moment curve. The reason is because all you need is to ensure that after the exponential transformation, you have the sufficient condition that you can impose on the transform coupling such that you guarantee that the transform coupling has a representation in terms of the moment problem, has a solution in your moment problem. Once the transformation has a solution in your moment problem, then the pre-translation, you can directly write down the spectral function for the pre-translation, which is bounded by the L. So that's why it's very robust in 1D. So yeah, so then yes, and the fact that the 2D map looks very similar. So yeah, I mean, of course, this is not an argument that tells you that it is suitable for any double moment. But yeah, but I wouldn't jump to conclusion that that's the thing to worry about. But anyway, so
Yeah,
Yeah.
I also tried looking at the kernel, but I couldn't figure out how to even get what it is, and then I'm also confused how to actually use it. But might
okay, that's I mean, the kernel is really only in this guy's paper, right? There's no other paper that.
So, he has a slightly older paper where he cites some things from the 50s, and there's some kernel there, but I think it's different. I couldn't do the map between them so far.
Okay.
Okay, so first, so let's just go over equal k just to have at least some constraint here. So
By the way, can we be a little bit precise? So right now, it is literally zk, right? Not zk minus 1 or
yeah, just leave it as k just for simplicity.
No, but it's a little bit complicated, right? Whether or not you actually have, I mean, I think that in 4D we exactly have, so that's why, so by the way, I mean, it's important, right? That whether or not your K actually starts with.
Yeah.
Yeah, so that's actually very important. That's why I really want to have all of this tagged onto the physics. So if I remember correctly, in 4D, it is literally K ZK. I think I wrote it in the note.
Wasn't it -1? I thought it was -1.
Was it -1? So let's look at the note. So we want to. So let's look. I guess you've been editing the note.
I added a few things.
So let me see. Yeah, it's sorry, it's G2K plus 1 is, yeah, so G2K plus 1 is ZK. So that means when K equals 0, which is G2 0, you get Z to the 0. And when you have G4 0, you actually have Z1.
For 40, sorry.
For 40, you have Z1, so Z to the 1 power. I mean, you guys can look at it. That's why I keep saying that it's important to make sure we're working with it. So if you look at equation 2.2 in the note, I've worked out the 4D case with the, and you see that it's G2 times K plus 1 is equal to ZK. So G20 is so G20 is Z to the 0th power, and Z to the first power is already G4. Yeah, so you see, so that's why I really don't want us to do like simplified mathematical problem, because there will be still be issues when you're trying to implement in the physical context.
Sorry, but so you're saying G20 is, oh, I see, 0, okay. But so why is it 2 times something? Because I want something like G30.
I mean, I mean, we can try to do that, but then the problem is that then you're I mean, we're redefining S prime into Z, right? Right. Okay, because right now when we're in the foreign limit, we know all we can bound is, because we have all we can bound is, oh, or maybe you're thinking about the A geometry, so that's probably better.
Oh, sorry, but you also have, you're using not mass squared, or
What do you mean not mass square? So
how do I get G30, for example? Because that would mean I need K to be a half.
Yeah, then I guess K is equal to a half. So then yeah, so then you just have Z. Right, then you, yeah, okay, yeah, so sorry, so I'm looking at the, yeah, okay. I mean, the first Z, I mean, there's a there's a redefinition between the first equality and the second equality. That's all there is. Yeah, so
Okay.
yeah, so either we stick with we stick with the first equality, or we stick with the second equality. Yeah, I was sorry, now I remember I was just trying to do things for just only the even powers. So that's why I stick that in. Somehow I remember, somehow the reason I was doing this was because somehow I'm worried. Okay, I think this is probably something that we should be careful about. Somehow I worried that because the proof, let me think, somehow I remember I was doing this because I'm worried that I really need to have the full moment, meaning that I need to have the full thing starting from U to the 0th power. Because you guys see that previously we don't really care about whether or not the moment starts with 1 or anything, because we can always absorb stuff into rho, right? But now since the rho is a positive, I mean we're bounding coefficients with rho, we cannot arbitrarily absorb stuff into rho to call it the new rho. So that's why I needed to have I really need to have everything start from 1. Yeah, that's the problem. And so therefore, if I have, okay, I think this is the issue, which is maybe this is already something that we need to worry about, which is that so if we start with, I mean, we can look at 2.1. So if we really start at G20, then our first coupling G20 is actually 0,1 dz Z, right? Because n is 2,
yep.
Right? So that means we're not starting from 1. And that was why I absorbed, but it's okay, because I can redefine dz as dz square, and z square as my new parameter, right? And then then everything is brought back to 1. But as Laurentio says, then what about the G3s? So
Mhm.
originally what I was doing here was I was just putting constraints. So here I'm saying that I can do constraints on if I just talk about, if I just consider G2, G4, G6, and so on and so forth. But okay, hopefully I convince you guys to not deviate from the physics problem, because anything slight changes now is I mean, whatever we work out for the math problem, I mean, we have to think about what exactly are we dealing with in terms of physics wise. So I think that it is, yeah, I mean, I think that you guys agreed, right? That, I mean, it is important to have, so first of all, is it important to actually have the moment starting at 1?
I don't think so.
Okay, so why don't you, so why isn't it important? I mean, you're talking about, so I'm saying you're bound, the derivations that you have right now are you're talking about a moment starting from 1, right? 1 z squared z cubed multiplied by rho, and then rho is bounded. This is the problem that you're solving, right?
Yeah.
Right, okay, but then that means I need to put the problem in your format. If my moment is not starting from 1, then what am I doing?
Well, you can just project out the lower stuff, like you project out the higher stuff. There's no difference between, if you're looking at, I mean, you could be interested in
Okay,
the
so you're saying that you just add auxiliary 1 stuff in front and
yeah.
you're axing out. Okay, but then when we're talking about projecting GK4, I mean, we need to, I mean, you have to know that your G4 is not really the G4 of the physics problem.
Yeah, sure.
I mean, your G4 is probably like G2
Yeah.
in the physics. So that's why I really want to have everything cleanly connected. So I know that there's a tendency to just start with this, let's assume this and then try, but I get kind of anxious anxious about that. This is not really the physics problem, and then we have to do it, and because then, yeah. Okay.
Okay, so let me see how I go back to the screen. Okay, so well, I mean, here just let me keep the same notation just so we don't get confused. So 4 here is 4 here, just for now. Okay, and then we have G42. And now what I'm saying is,
Sorry, just Z4. Okay, I see. So this in our context would be what? Would be like,
I think it's 3, but again, yeah, I mean,
okay,
that's the way I work it out.
Yeah, so then there's no crossing plane here.
What I mean, the crossing plane is, if this should be 3. I mean,
No,
this is,
I mean, your G40 is really our G3, right? Your A40 is really our A3. Because our
no, so I mean, in totally everything super physical here, this I think is what you need to do. This, at least to get the same like powers and everything as Simon does. So A40 or G40, this one is the same, is with a power of 3 here. And then the null plane is just as before, it's like this.
Sure.
Okay, so now I'm saying that, so this one is the same. So this is at equal k, and I'm saying you can treat this as a single moment, with the difference that you integrate over this part, basically. So basically you just, because if you have rho of j, z.
So what is the bound? I mean, it's a single moment, and what is the bound? What is the statement of the bound?
So if this were a single moment and I had like A0, A1, A2 given by some j, pi, ji.
So the bound is just z cubed 0 to 1 integrate and multiply by 2. That's what you're saying the bound is.
Yeah, you basically do this integral and you get some extra factor of 1/4.
Right.
So now I'm saying that the geometry of A4Q is exactly the same as the geometry of like single moment in Q.
Right.
Here.
Right.
But instead of having P less than say L, now you need to do P less than L over 4. That's the only change.
Right.
And this is necessary and sufficient.
Okay. So what happened to the 2j plus the 2l plus 1 factor?
Yeah, that's also should also be in there. Then if you have
Sorry,
this,
sorry. Before going, so what happened to it? I mean,
so
can we be
yeah,
precise?
here I
about
didn't put it. So what happens is, say if I have this simple couplings, I get some polytope with some vertices as usual. If I put in the extra factor of like 2L plus 1
Uh-huh.
everywhere, then you just get a different polytope with different vertices. But you can work out exactly what it is.
So first of all, so the fact that you have polytope here, so this is not implementing conditions on your exponential map, right?
Yeah, because it's all equal k. Yeah,
What?
because it's all at equal k, so there's no. So far, this whole z dependence is trivial here. So I can
Yeah,
just.
okay, and then I'm asking about the other direction, which is that you're saying that when you're talking about discrete, you cannot use the exponential map.
Yeah.
I mean, just a single moment with discrete, you cannot use the exponential map, is what you're saying.
Yeah, there's probably some way to get some continuous result that envelops the polytope, but that's not super obvious how to always do it.
So sorry. So here you're saying that, so what is the polytope then? I mean, how am I determining what the polytope is? Is the polytope the original cyclic polytope thing?
No, it's different.
Yeah,
so,
yeah. Good. So what is the polytope? Yeah. Well,
I have it in one of the notes. Let me see.
and do you know why those are the boundaries, or you're basically saying that it's you're basically saying that you do numerical analysis and then you find that you can approximate it by that analytic polytope.
No, so you can find the boundaries analytically, going spin by spin. So you put in spins, you find what the boundary is, then you put the next spin, you find the next boundary, and you find it basically.
Okay, this what are you? Yeah, can you tell us a percent? What do you mean by spin and find your boundary? Yeah, I don't know what that. Can you?
Let me share the other thing.
Thanks.
Okay, so here it is. So first you start with, you have two spins, like two states. So say for example, like a half and 1. And then the way you solve analytically is you just plug those in here. You solve for P.
So here, what is being bounded?
A1, A2.
No, I mean, what is P is being bounded, right?
Yeah, P is bounded by
Okay.
2.
Okay.
I think.
Okay.
Yeah, so you solve, well, I guess, no, sorry. You plug in x1, x2, right? And then you just solve for P1, P2 in terms of A1, A2. And then you ask that the solution is below 0 and 2.
Mm-hmm.
And that gives you this region.
Mm-hmm.
Then you work out exactly what the boundary is.
Right.
And then you go to higher n. So you add 3 states, you do the same thing. So for example, here you have like 1, 2, 1, 2, 3, 1, 2, 3, 4, and you always solve this.
Right.
And it's always, you just add like one extra boundary to the polytope. And it's fairly non-trivial. This is what it is here. So it's not a usual cyclic polytope.
Right. And when you have, so this is how many? So this formula, equation 10 is for how many spins?
It's for any number of spins. So you just plug in whatever spins you want. That gives you the corresponding wall.
Okay, but do we know why is it that?
No.
Okay, so that's what I'm saying. You're using numerics and then you're solving it and then you find the analytic the representation for that boundary. So this represents, sorry, so this represent equation 10 represents all of the boundaries and all of the boundaries that you draw, for example, for the blue one, this represents all of the boundaries.
Yeah, yeah.
Okay, cool. So okay, good. So now I put in 2L plus 1. How does equation 10 changes?
I didn't work it, or yeah, I don't have it written down, but you just modify the vertices basically. That's all that happens.
Yeah, but what, I mean, well, how do you modify the vertices?
Well, there's a formula, but I don't know how to like justify it.
Okay, can you at least write down what the formula is? I mean, what is the formula? Is it in your note?
It's somewhere in Mathematica. I don't have it written out.
It's somewhere in Mathematica.
Yeah, I mean, I didn't write out what the polytope is. I just know what some of these points are, and then I have to work out like what the pattern is, and then from that work out the polytope.
Okay.
So
Can you?
basically,
I mean, I think can you do that? I mean, can you just write down what the? I mean, this is good equation. I mean, once you have we have equation 10, we could probably try to think about why equation 10 is correct.
yeah, there's probably some reason, but yeah.
But we need the full thing. So can you just work out the? I don't think. I mean, it's just that. Okay. So what is C? C is the bound. I mean, can we, yeah. Okay. Maybe
Yeah,
some of these things you can start to import into the so that we can actually have a consistent notation throughout.
Yeah, well, I'm still trying to make to figure out what is like super correct here and what is still just in progress before I put it in the main note. But yeah, I think this is.
Sorry. So here the statement is this is. I mean, we should be able to understand this, right? So. Yeah, it'll be good if we could go one extra, if we can go to 3 points, because we have this 2j plus 1, then 2i plus 1. I mean, I guess if we go to the third column, we can see what the pattern is. I mean, at least what this polynomial and
And by the way, actually, this is not like the usual polytope also because this is just A1, A2 space.
actually, can we? I mean, I guess one way to see why this is. I think one way to see why this should be correct is you can just plug in A1 and A2 in terms of the convex hull with some P.
Right. Yeah.
Right, and then you just take the determinant of this and maybe you try to write it in a manifestly positive form.
Mhm.
And then maybe this determinant is just reflected into some positive thing with something like P minus something. So you know that if any of these P's are negative, then this is no longer definite positive.
Mhm.
I think that's probably the way to understand what this formula is. Yeah, because this formula is supposed to be if A1 and A2 is any of these vertices and that are outside that are outside yeah, then this thing can have negative. Okay. Yeah, yeah, okay. So you're saying that if you put in okay, but it'll be good to know. I mean, what exactly is the formula, just so that we're not just saying things from what the graph or what the polytope looks like. Okay, so this is
Okay, yeah.
so naively there's the continuation of so naively there's a continuation of A1, A2, and then higher, right? What is the analytic formula for the hierarchy? Yeah, this is okay. This is cool. Okay.
Okay, and now, so what am I showing? Okay, so this was for equal k, and now if you try to do equal q, so let's see. Okay, so now if you want to basically do this in the same way, I guess what you want to do is write out this, let me think. Yeah, so this is going to be like 1. So you write out the spins. Let me think. So let's write this one out.
Sorry, so is this, you want to do spin truncation?
Yeah, so I want to basically see what the equivalent is if I try to do this, derive a single moment condition from this, like I did here. So here I integrate
Yeah, you integrate Z,
this
Rho,
part.
right? Now you just want to sum over J.
Yeah, so let's just say I start from spin 1 to be 1Q, 1C. Then I say L.
Yeah, so I guess, yeah, but then you cannot, you're trying to say, then you're trying to pull the rho JZ as 2 outside as well, right?
Yeah, so now,
You want to, so now it's like 1 plus 2 plus 3 plus L to the Q
yeah, it's going to be,
multiplied by 2, right?
yeah, so now this is saying the equivalent thing is,
No, multiplied by 2, you're putting rho Z as 2 out.
oh, okay.
Yeah, so then that, so that's, but then there, yeah, or I'm not sure this is what the, yeah, I don't know what this is anymore.
Yeah, this is less clear. I was doing some checks and it seems like the equal Q problem is the same as the single moment continuous, but instead of being on 0, 1, it's something on the equivalent thing is like on 0, L to the Q, where this is the max spin. I think this was the, like at least the numerical answer. So if you do, yeah, equal Q is basically this.
But then, sorry,
Yeah.
but then if you take L to infinity, then it's just a 0 to infinity, right? So we might as well
Yeah.
just, so you're just saying that it's the bounded problem at 0 and infinity. According to what you're saying.
That, yeah, that's right. Yeah, so in any case, the only, yeah.
So that would be the exponential thing with the, and then you impose the Hankel and the shifted Hankel on the expansion.
Yeah, although I wonder if this is, yeah, sorry, I'm not sure this is the only thing. You might need, I'm not sure you have to rescale, like P is now smaller than some L with something else. Yeah, I have to be more careful about this one. But the point is, you can do this, treat it as a single moment. But now the problem is, I don't know how to do single moments from stuff like 1, 1. Let's just do the simple continuous in both
Yeah,
directions.
but I mean, but I think I okay, sorry, but it probably is just me, but yeah, I don't think we have the ability to nail down the double moment unless we have the single moment really nailed down, because the double moment is a product of stuff that is just not the same nature, right? I mean, there are two moments that are not the same nature, and right now it looks like for the single moment of different nature, you're doing very different things. So
Yeah.
before we nail down exactly what to do for the single moment, I'm not even worried about the double moment, the double moment problem. So, right, because actually, yeah, because yeah, so it seems like this L dependence thing is really killing us, right? I mean, we're not killing us, but it's really making things not so trivial.
Yeah, it's very different from the old problem.
Yeah, I mean, I mean, said in another way, the reduction of the double moment problem to the single moment problem is now no longer trivial. I mean, that's fundamentally the issue. So previous, we have a two moments and we can always look at the single moment, but that's because the other moment we can always absorb into what we mean by P. That's fundamentally what was doing before, right? Now you cannot just yeah, because your P is bounded, so that forbids you from arbitrarily absorbing these things into P, which is what is the problem, what is causing the problem here. Is that you have to, even though you're dealing with a single moment problem, but you always need to take into account what that extra P sitting beside you is doing, which is really the complication here. And of course, then how does that extra P looks, or the extra piece looks like, is going to influence heavily on what you're supposed to do. So yeah, so that's why I like to stay within the context that is closer to physics as possible, so that we're dealing with yeah. So okay, I guess it's still work in progress, but maybe we can at least have the Q direction. Maybe we can understand that. Yeah. So if you have more analytic format, then we can all look into what those boundaries supposed to be. So there's the you want to augment it with the 2L plus 1 and see what that vertices, and then maybe if we can do one step further just to see what the patterns of that. I think we could probably write down. Even that solution is actually cool. I think that will be probably something new. I don't know, maybe not even mathematical literature has that. That we develop, or what the bounded problem looks like. Yeah. Okay. Yeah. Do you have something else you want to talk about?
Well, I mean, just if you want to go a bit over the paper with the double exponential thing.
Yeah, I haven't had a chance to work through it yet. So I don't have any much to do. Or did you have some more comments that you can tell us?
I have just maybe someone understands something. I don't know if I'm just not getting it or what the point is. Let me try to share it. So I think it's here. So actually, so this guy has two papers, right? One is like a two-dimensional moment problem.
Mm-hmm.
The other one is the L problem, and this one is later. So let's see. So here, Oh, and by the way, so for all of these things, the boundaries are simple to understand. So that's always like a helpful thing. It's always like the interval function where it's continuous on some interval and then 0 everywhere else.
Sorry, what do you mean? Sorry, so what boundaries are all in
The boundaries of all of these things, all of these like continuous things, it's always the interval function where p is the maximal value up to some.
I see. This you mean the boundary, the boundary solution, the row living at the boundary.
Even in the 2D case. So I tried some numerics on the 2D case and it's still something like that. Okay, so yeah, so here he defines this kernel. I don't get what he means by this notation, basically.
The bar.
Yeah.
So we have this define, let the kernel. So the first, sorry, so the first one is the first one, meaning just that this kernel is going to be invariant if you shift on some lattice.
This one?
Yeah.
So this one is saying, so this thing has 4 indices. So theta is 0, 0. So that's 0, 0. Alpha then is mn. So this first line is saying that 0, 0, mn is equal to bmn, which is what you get from here. And this is also equal to like 0, m, 0, n. So these two are equal.
0, m, 0, n, is it?
It's also
I see.
So this is what this line is saying, but yeah, I don't know what this can possibly mean. So if this is a 4-index, I don't know if it's even a 4-index tensor or he means something else. That's
this is the first place where bar.
Yeah, as far as I can tell. I mean, he has it here, but I guess here it's
Where?
Here. So I think this is a matrix as well.
So could it be just complex conjugate? Because this is mapping, so k delta is supposed to map n squared times n squared into complex number, right? So that means k delta is complex.
I see. So he gets.
Yeah, so k delta is supposed to map, yeah, the n squared to some complex number. So the kernel is giving us a complex number back, right?
Right.
Where b alpha, so b alpha is a complex. I guess these b's are supposed to be complex. Are these b complex? I mean, they could be complex, I guess.
You mean alpha and beta? I thought these are just some points on the lattice.
No, b alpha. I mean b.
Oh, this guy. Yeah.
Yeah. B and m can be complex, right?
Yeah, I think so.
Okay, yeah. Then k, yeah. So k is like acting. So k is just something that acts on these mn pairs of indices that converts any pair of indices to some complex number. So I guess k. I guess he's. I mean. Yeah, but okay. I guess he's defining this because I mean we would say that we just care about b. Well, why do we want to give a function that gives b? I guess he's trying to make this a function, so like more like a distribution, something.
This k. The point of this k is that then you ask k to be positive semi-definite.
Uh-huh.
And its entries are going to be these polynomials in B. So it's like a more general Hankel, I guess, right? I think that's the point of this thing.
I see. Oh, okay, I see.
Yeah, well, and yeah, I was trying to solve this, but I didn't get any solution. And then there's another problem. I don't know if it's a typo. So here he has alpha. Maybe it's the same thing. So here there's an alpha, but if you go to his second paper, here he has beta. Oh, can you see this?
No. Is it in your?
Oh, I
Browser.
can't switch tabs. Yeah, well, sorry. His second paper has the same definition basically, but some alpha is switched with a beta. This one.
I see. So so equipped with this kernel, do you see what is the condition? Is it then simple, just use the kernel to write down what the condition is?
Yeah, I'm also not sure about that. So he says, yeah, so you want K to be positive definite. But so yeah, now you have this 4-index thing that you want to be positive semi-definite.
So do you see where he says what the constraint is? Or maybe it's in some theorem. I think I see a theorem below. Yes, so what is theorem 2 corresponds to? If and only if AMN is the exponential map, the result of the exponential map, right?
AM are the couplings.
Oh, it's the before the coupling.
Yeah, and this one is fine because he's using Z and Z bar, so it's fine for us if we do real.
So K delta is acting on the original coupling A.
Well, K you can express in terms of A, right? Because, so, sorry.
Sorry,
so
B is the original. Oh, sorry.
So, yeah.
So
these
A
are
is the original coupling and B is the expansion result, right?
Yeah.
Oh, sorry. So K is acting on B. So K is related to B.
Yeah.
Okay, so the condition on B is basically stated as the condition on K, right? That's basically.
Yeah.
Okay, I see. Wow, this does not look straightforward at all. I have no idea what this. Okay, I really need to. So and this paper, yeah. What do you want to say?
So I tried to solve this. Let me. So it shouldn't be that hard, but I don't know if I'm using.
Sorry, I'll be right back.
Yeah, just fine.
Sorry, guys. Okay. Oh, you're solving the,
Yeah, so here I'm trying to solve this thing. Anyway, you can solve for some of these, but not all of them. So that's, yeah, one thing I don't really understand.
you mean you're trying to solve that the K becomes the kernel becomes a function of the B's?
Yeah, so the way I think you can do this is, so first you use this definition for K. And then this one. Yeah, so, well, anyway, you can solve for some of them and you get, okay, so then you get this 4-index thing. So then I don't know if you just require this to be positive semi-definite. And I also don't know how to solve for all of these things.
Let me think about it. Why isn't it? I guess, I mean, if I mean, if let's say if both of the moments are just positive, are just, for example, on the positive real axis. Let's say if we do our previous proof for the single moment, and then just do it for. So I would need to think about what went wrong if we do the exponential math. And I mean, is it just that for the double moment we don't have the? I mean, of course, as we know, right? It is very important to have the. It is very important to have the sufficient condition because it's a crucial step.
Yeah.
But we do have the sufficient condition for the double moment, right?
Sorry, for this bounded?
Or no, or for I mean the previous proof for the exponential map for the bounded problem was based on the, as I mentioned, it was crucial to have the to have that you have the sufficient condition for the single moment, unbounded single moment problem. So naively, I would say that if we have the sufficient condition for the unbounded, here bound or unbound is referred to the spectral parameter. If we have the sufficient condition for the unbounded spectral parameter double moment problem, then naively the same proof will work.
Sorry, I don't see why. Because this is more constrained, right? It's a smaller space.
No. I just mean the same original. No, what I'm saying is that the original proof for the bounded single moment problem. Remember, I derived the proof,
Yeah.
and that proof only. So I mean, we can. Let me share screen with you guys. So, but although I need to find where exactly did I write it. All right, here. Okay, good. So here, good. So let me share screen. Yeah, so I think, yeah, so I mean, if we just go over the original proof. Right. So remember that previously when we were proving this, so let me just use, right. So we're saying that if the important point was that we have the sufficient condition. So actually this goes to infinity, because this is an exponential, even though this is finite, but after the exponential map, this goes to infinity. There's infinite powers of these things. So the statement was that we impose a Hankel the corresponding Hankel condition that ensures that all the T0, T1 to T infinity are set in the it sits in the moment curve of whichever, either it's the half moment curve, blah blah, whichever. So we just impose a sufficient condition on the on T for the unbounded problem. Then we're guaranteed to have the S0 to be set in the bounded problem. And the proof was very simple, right? If we can impose this, the sufficient condition on T that corresponds to, that it sits in the solution for the unbounded problem, then that means T is written, has a representation in terms of this with some rho where rho is unbounded, right?
Okay.
And then we went through this, and then we see that we can construct the rho here, which it satisfied the bounded rho. And we can show that, and then it's just putting things back in, and then we show that this S here is given by the bounded rho problem. This is given by this rho where the rho now is bounded.
Right.
So is naively, wouldn't naively we say that we have if we have the sufficient condition here for the unbounded double moment problem, we will probably reach the same conclusion.
So you mean just double the things, so you have some exponential of S, Y, J over X?
Yeah, exactly. I mean, the exponential map that he has there is literally this thing squared, right?
Yeah, I think I tried that a while ago, but I need to recheck, and it was too strong. If you just try to impose the double moment on this new expansion. But I'll check again to make sure. Yeah, that's what I was thought, but something went wrong.
Yeah, okay. Maybe we can share. Then let me just run through this argument. Yeah, okay. I think let me type this argument up for the single moment problem. And then let me just generalize this to the double, and you guys can see what is the issue. Maybe you guys can spot if there's any issue. Because naively, like I said, all you need is just the is really identifying that this is the map, that if you have if you have some solution here with the unbounded problem, you're going to find a solution for the bounded problem here. So let me type this up, since I guess if we're writing things up, we'll probably need to have this as a proof in the appendix anyways. So let me type that and see what the generalization to the double moment fails. Okay. Sorry, did Hudson drop out?
Yeah, I think so.
Okay, maybe while we wait, do you have something to discuss?
Yeah. Sorry, I have to go to the restroom. Sorry. waiting for a moment.
Okay. Yeah, I guess we should also probably see if maybe Hudson or Lee will have time to do this. Is to really scan the other EFT hedron space to see what this STU, how much the STU amplitude occupies this space.
You mean in higher dimensions? Like
No, I
higher-
mean, you mean higher? Yeah, higher K. Yeah, the EFT, not just G3, G4, but in another. Hey, Hudson. Hudson, are you doing SDP? Further doing SDP for the masses case?
Yeah, and
So did you find anything
Yeah.
interesting, or it just becomes more and more fragmented as we discussed last time?
so maybe let me share my screen.
Okay. Yeah, Li Yuan, let Hudson go first.
Yeah, sure.
So, alpha and gamma are XX and YY, beta are XY. And so first of all, spin 0 in alpha gamma and spin 0 and spin 1 particle don't contribute to the no constraint. It just give us 0, so we cannot constrain that. And this one was mentioned last.
Spin 0 in alpha gamma and spin 0 spin 1 in beta, right?
Oh, sorry, yeah, beta. Yes, in beta. Okay. And spin 2 must exist and in alpha gamma, and this is mentioned last time. And so the second statement is if there are only 2 spins in alpha gamma, that is 2 and some A, and A is larger than 2 and A is even. And beta must have member in both this set and this set. This means that if I only have spin 2, spin 5, spin 7, then this doesn't work. I have to have members from this set too. So, for example, spin 2 and spin 3.
As a valid combination, but 2 plus 4 is not valid. Ruled out by K6.
Oh no, yeah, yeah. Okay, and if there's more than 3 different spins in alpha gamma, then there's no restriction on beta. Yeah. And at k equals 6, I think this will further branch this out. So I think we should stop at k equals 5.
Okay. So as Leeway said the other time, it seems like you. So he was looking at EFT space, right? So I mean, what one of the things he was doing was he was bounding the, and even SDP couldn't give that answer that I wrote down, which is just very simple.
Right.
So let's think. So that probably means that these conditions, the fact that SDP didn't even get that simple result that I derived, means that the equations that we set up here are not actually the full story. Right. The equations that we're
You
setting.
also need to include the like 1 massless 3 massive. I think maybe that's also included when you do the linear combination.
Yeah, let's. Yeah, let me just to make sure that of course, yeah, that is naively a possibility, but
Sorry, which result are you referring to?
no. So didn't we weren't we?
Maybe I missed the.
It's you know in the paper that I wrote, there was this inequality. Let me just. share screen with you all.
Oh, you mean the superposition of states?
Yeah, the superposition of states. Yeah. So yeah, multiple species here. Yeah. So this was just a trivial superposition of states. We say we have. No, actually, you see, we assume that there's only A4, A squared, B squared, and B4. So that's so the amplitude that we've written here is exactly the same set of amplitudes that we're working with. Yeah, and then somehow we can derive this bound where Dewey couldn't derive it from STP. So the fact that he couldn't derive it, yeah, probably sounds like I think that probably sounds like what we're not thinking about. We're not using the whole constraint right now.
Sorry, are we using the expression relation for M? Or,
You mean here deriving this bound?
yeah. So we assume,
well, in a sense, we're assuming dispersion relation because of the fact that, I mean, we're assuming that MABBA and the 4 limit is positive. That is dispersion relation, right? But this, so the statement is that MABBA is written in which is organized in this, and of course, we're assuming that this is the S squared part. We're just looking at the S squared part. So this condition is just G20 is positive.
oh, okay. Hmm.
Actually, even if this would be cool if we, no, I just realized that yeah, I mean, once we figure out, I mean, once we finish our, so once we worked out what can we get from the spectral function, where it's positive, I mean, that is bounded from 2, then this equation will be even interesting, right? Because this equation was just that, this just came from the fact that the things had to be positive. So now the thing has to be positive, but then smaller than something, there's an upper bound now. Right, so that means that this will be also be bounded by upper bound. I think that will be super cool. It might be, I mean, these bounds might start to become really useful conditions. Yeah, but speaking of upper bounds, and so I think that we should really start to look at these. So maybe we should, in the massless case, I think really what we should do is we should let's think a little bit. Yeah, it'll be good if we could. By the way, Hudson, are you guys in Taipei?
No, I think I'll be back 1 to 2 weeks. Yeah, I'll be back in Taipei.
In 2 weeks?
I think so.
Okay. Yeah, it would be great if we could, after you guys get back, we could just really, you know, everybody sits together and then we just work on the blackboard and see what constraints we can have. I mean, yeah, okay, maybe. Okay, we'll see about that. Maybe we'll see how the pandemic situation. I mean, it's dying down a little bit, so let's hope that it gets like to 0 for a couple of days, and I guess we'll be feel more comfortable about. But I think that, so there's a few things that we should do at the masses mix. So of course, there's this, and then so I think that we can start to think a little bit about. I guess, Hudson, do you know how to? I guess you can start to work a little bit about bounding the EFT space. Like
which phase?
The EFT coefficients, so like these C's and D's and
Oh, okay.
yeah, and we can set up the also bounding the spinning space as well, the masses helicity space. So this is related to what I wanted to ask. So you guys see that you guys see that there's been discussion between me and Laurentio, and I asked that question, right? That if the G3, G4 space is spanned by 1 over STU and 1 over S and the scalar amplitude, which means that in that space, any EFT is basically the combination of these objects. Then it looks like most of the space has large spin dominance. I mean, but of course, as Laurentio said, this is just G3, G4. We don't know if they actually span the higher dimension space yet, meaning extra. So that's something that we should understand. And I'll probably write up like a few notes on a few things about. I think we should. I mean, we can go in different directions to start to probe these questions. But I think that we should understand how much the STU. But because G3 and G2 is not special. And as you know that if you go to higher dimension, I mean, you guys saw the tortolia. What was it? He has a 3D plot, right? He called it a tortolas, or I mean the Mexican food thing.
Oh, the tortilla.
Oh yeah, tortilla, yeah. Okay, yeah, but it's very flat. The point is that it's very flat, right? So it's really just that 2D space just that like grow a little bit, right? Do you guys know what I'm saying?
Which graph?
Okay, let me just call out the paper. 1 sec. I always spell it wrong. Is it HUOT? Yeah, HUOT. Yeah, I'm always amazed once I open Simon's paper. Like he has these huge papers and like half a year, 6 or 7 of them. But he looks like a person that enjoys life. So I don't know how did he get so much done. And he attends lots of conferences as well.
Right. Yeah.
Yeah. So yeah. So so I guess he has this space, right? This is the G3, G4, G5. So yeah. So you guys see it. I mean, it's very at least in the 3 dimensions. Really, this is really thin. So since in the 2-dimension projection, most of it is G3, it's the STU. So I will imagine that even in a 3-dimension, most of it's going to be filled out. But yeah, but we'll be good to understand. But if it fills out most of the space, so this is what I'm trying to suspect. I mean, and which is basically that in the talk I've been saying the wrong things. So in the talk I keep saying that the geometry is imposing a low spin dominance, but the low spin dominance, the low spin dominance imposed by the geometry is not really that sufficient. It's really close to the real thing. But I think I was saying something wrong because the examples that I was bringing up was the ODFT Hedron paper, which I was not putting the higher K constraints in. So here we're really imposing that the higher K constraints that projects down, and once so and in talks I always draw this EFT Hedron paper where we have these flat and then these theories are like in tiny corners, right? But that graph is actually, I mean, it's not like this curly graph, and that's the reason is because it's just some fixed K intersecting polytope. That's all I'm imposing. I'm not imposing like the higher K projecting down. So that's why I get these sharp boundaries, and then in that sharp boundary, yeah. The thing looks and that's also similar to what Zvi is doing. They're also just putting fixed K, and that's why they have these sharp polygon graph. Whenever as you guys know, because whenever you're really projecting higher K down, the graph you should get is like these curly graphs. And so the blah blah that I keep saying about the high spin dominance is not encoded in the geometry. We need something more. I kind of feel like now I realize that that probably is not wrong, but it's not correct, because at least from this, if we project the K down, it's covered by two theories which are obviously high spin dominance. Yeah, so that's why I was suspected. So I think we should make the and that's why I kind of feel so after I gave the talk in the positivity in the positivity conference and then in the discussion section, I was asking, you know, why is there some other way we can import high spin dominance? And I kind of feel like Simone is completely uninterested in that question. And now I'm trying to, I kind of feel like probably the reason that Simone is uninterested is because it's not really that much of a mystery. It's actually in the geometry. I just keep saying the wrong thing. But at least in this G3, G4 space, it looks like it is in the, it is most of the region in the geometry is high spin dominant. And the counter example that I was giving was not really giving the full geometry. Yeah, so I guess that's really unfortunate that, yeah, I mean.
I would say it still depends what, I mean, you can always impose stricter higher spin dominance, maybe like to what string theory has. I don't know if string theory has stronger spin dominance than this 1/STU.
Yeah, I kind of feel like that's also that I can analyze, and maybe we can chat in a couple of days. I can show you guys the numerical answer. But I kind of feel like it's not going to be more so, because I kind of feel like the high spin, the most dominant contribution, the most dominant is supposed to be the thing that we have. Because if I plug in string theory, so if I plug in string theory, or which I did before, and then if you look at the space, it's always going to start here, but then it carves in here very fast. It goes in here very fast. So string theory and also the one loop massive box, it all curls in very fast. So and it seems to be very hard to get outside here, and you can see that, I guess. Yeah, I guess to get outside here, what you want is you want a higher. Yeah, you want to have higher G4, G3 ratio, right? Because that means you want some very high G4, G3 ratio to be a little bit higher. So you want to push up the G4. Yeah, so it's really hard for me to penetrate this barrier here. So I kind of feel like this seems to be setting up some kind of yeah. But anyways, we should. I'll have more to say about that probably in a couple of days, and I can show you guys what I mean. But yeah, I was just saying it would be good to just see how maybe we should think just see about how these things span this space. Yeah. So that's what I think. What I say, that maybe high spin dominance is already encoded in our geometry. That's what I suspect. Yeah. Yeah, but if it's encoded in our geometry, we should probably, as Berntio said, just have a well-defined notion of what that does that high spin. I mean, to quantify what that dominance is. Okay. Yeah. So Yuan, did you have something to share with us?
Yeah, but before that, I actually have some question. I really want my tablet to join this meeting, but I failed last time. So maybe I can try it again. I don't know how to set up the audio. Let me find a link. Sorry, let's wait for my tablet. Yeah, I was thinking, so So in the old paper, using the superposition of states, so we scatter alpha A plus beta B, right? And the four external legs are all the same state. So we have the full permutation symmetry. But I would just
There we weren't even, I mean, at least in the old paper, we didn't even, sorry, in old paper, you mean the paper I had with Nima?
oh yeah, the
Yeah.
paper you just showed.
Yeah, actually, we didn't even use cross-view symmetry because we just do one superposition as in alpha, beta, and the other superposition in terms of gamma, delta, and then define big A and big B. And so we're just using the positivity of big A, big B, big B, big
Oh,
A amplitude. So we're just using that as positive.
yeah, I was just thinking if if what this is doing and what STPB our setup now for the mixed bootstrap are talking about the same thing.
Uh-huh.
For example, do we actually have like a reason, a rationale for having a dispersion relation for M for alpha A plus beta B comma delta, for superposition external states?
Yeah, I mean, it's just a state, right? I mean, in the end, your S matrix is just a scattering element of states. I mean, it's,
Right.
Yeah, so
Yeah.
it's just a
Is
state.
it already assuming? Is it? Oh, maybe. Yeah, I was just worrying about it. Is it already assuming that the UV states contains only those that interacts like simultaneously interacts with A, B, C, D, or
No, no,
is there some stronger assumptions
no. That's the
within?
point. It's not. I mean, it's just a I mean, it's just a. I mean, it's just a change of. Yeah, like, as I mentioned, it's just a change of. You have two in one frame. You have two. I mean, it's literally the statement that the fact that you have two states A and B that are both massless, unless you have some extra quantum number, but if you don't have any quantum number, then the choice of A as A, B as B is not invariant choice. You can always define new linear combination. So this is literally saying that the physics should not depend on your basis.
Oh, okay. Yeah, that I agree. Oh, okay. So last time Li Wei said that when maximizing some like for example G31, so and he looked at other couplings to see what is the space allowed for the other couplings, yeah, other than G31 or A31, and he found that the space is actually very small, right? Then I think it can be geometrically interpreted as where the optimal vector, A vector, for maximizing A31 actually sits at the corner of the EFT hedron, right? Because maybe I can draw it on my tablet. How do I share screen?
But there's a green button in the bottom.
Okay. Oh, okay, I found it. And so, for example, we have some convex hull, the EFT space, then we can, so we're maximizing some variable, for example, A31. So these lines I'm drawing is the counter lines for A31. So maximizing A31, we're going in this direction. And finally, we hit this corner. So if the optimal vector for maximizing this target objective function A31, the optimal vector, if it sits here, then in the direction perpendicular to A31, then yeah, there's very little space for other couplings to allow it to move, right? But so it's like saying that. So okay, so first of all, these boundaries are defined by the conditions being positive. So these are the intersections of the contour lines for G equals 0, right? Like G equals 0, we can draw some contour line and we take the intersection for different I, and then we obtain these boundary lines. So I think it's saying that the counter lines for A31 is it's not parallel to any other counter lines for GIs. Yeah, it's just some fancy way of saying that we're actually arrive at a corner of the convex hull.
Right. Sorry, what was the question? Initial question again? Can you?
Oh, sorry. Okay, I didn't say it clearly. Okay, so so for example, we are maximizing A31 in the space A20. We're introducing other UV couplings, for example, all the way up to A53.
Uh-huh.
So this vector, I call it A. So it lives in some convex hull, a higher dimensional convex hull. So maximizing the function f equals A31 actually, and that we can find an optimal value that has the largest A31, and
Right.
that optimal vector actually sits at the corner at the convex hull. Then fixing A31 and just looking at the other couplings around this point,
Mhm.
then maybe we can see what Liwei said, that other couplings are not allowed to move in a large space. They're restricted because the counter line of A31 isn't like
Sure, but I mean, but
Yeah.
what if you? I mean, what if? Yeah, I mean, it is possible that A31 doesn't lie on a vertex, right? It's possible that A31
yeah.
a
So
curve boundary. That is that you can draw a curve boundary, and the A31 is just going in this direction.
yeah, maybe.
Yeah, I mean that was a mystery. That why is it that why is it? Yeah, so to say and exactly to what you're drawing to say in another way. Well, yeah, why is it that the maximal A31 is sitting at a vertex? I mean, because all we require is that it has to sit at some boundary. But the boundary doesn't have to. So the real statement is that let's say if you have crossing plane, which is 2-dimensional, why is this sitting at codimension 2 boundary? It could have sit at
Yeah.
codimension 1 boundary. So that's really the question.
Yeah, because I also find this numerically that we're maximizing some couplings. We always arrive at a unique solution, not like multiple minimas. Minima.
Right.
Yeah. So
No, this is an important question because
yeah.
actually what you're observing here is observed all over the place. So we, as you know, that we're looking at another problem which is related to partition functions, and we're maximizing the value of the partition function at a particular point. And there, the solution is also starting at a vertex, and we're actually using that information to find the solution. That we're assuming that, so we're assuming that the solution is starting at a vertex. We find the solution. And then we compare to the STP result. The STP gives us the same solution. So we know that the maximum value is always sitting, but we have no idea why it's sitting at the vertex. So I think the fact that we don't have any idea why it's sitting at the vertex probably tells us that there's some aspect of our problem geometry-wise that we don't fully understand. We're not fully appreciating.
Okay.
Yeah.
Okay.
But-
Yeah, maybe I can share the share my
But do we
computer
know
screen too.
for any other point?
What?
So do we know that this is not true for every other point on the boundary? So here you're basically saying that at this upper corner, there's no line that's sort of, I guess, perpendicular to this plane, right?
Yeah.
So that there's
Yeah.
no, and just when you project, it can have any value, but always projects down to the same point. But generically, that would seem to be true for any other point, right? It's
Yeah, we should check that. We never checked that for the partition function because you you only care about the partition function at the it only has meaning when you have the partition function. Sorry, we were expanding the partition function around the beta equals 0, which is like temperature, self-dual temperature point. And that's the point you care about the partition function. But yeah, I agree. We should check this by maximizing the different couplings. I agree. Is it that the different couplings always sit at a vertex? I don't think it will always sit at a vertex, but anyway.
Okay.
Yeah.
I don't know how to switch off the screen sharing. Maybe I can go back to Zoom. Oh,
It just stops. Yeah.
okay. So I modified my program to I sped up a little bit so that it can handle more couplings. in higher dimensional space.
Wow, okay.
So can you see my Mathematica?
Yeah.
Okay, so we want to include A6 also, right? Because previously we're only considering up to A5. So for A5, the space of A20 all the way up to A53, this space, I'm not listing A53 because it's related by 2 and 1 by the null constraint. So for this 8-dimensional space, it's actually bounded. A52 and A53, they both have upper bounds.
Mhm.
So we have a finite space, and in this space, my method can work pretty well. But when I introduce A6 couplings, the first problem I encounter is that A64 when we're not imposing the A6 K6 null constraint, A64 actually don't have an upper bound. So the problem is that, okay, so recalling that we were actually maximizing this function, right? The target that we want to maximize plus some barrier function, which is a log of product of the positive constraints and Hankel constraints G. So the product of these involves A64, which doesn't have an upper bound. So the log of these products actually don't have an upper bound also. So it using whatever method to maximize this function won't give a solution. It won't converge to a point that makes this function maximized. So yeah, if we introduce A64, then my method simply doesn't work.
I see.
Yeah, because we can always make A64 larger so that this has an even larger value. So it doesn't converge to a point, an optimal vector in the A space. So I just step back and rethink. Maybe we can ignore A64, but then it's not a complete geometry, we know, right? So the constraints that we have are these. This is for the big matrices. We have to start from A20 and we have these matrices all the way up to some A6. So I'm including all the matrices that involves, sorry, yeah, all the matrices that involve only up to A6. So we can have larger matrices like this that also involve 5, 6 in these matrices, but it involves also higher case. So I just ignore them. So this is how I do the cutoff. Okay, so we have to consider the big matrices starting from 2, 0, 3, 0, and 3, 1. For infinite dimensional matrices, these are enough. But
Sorry. Okay, Hudson, you go first. I'm just complaining about the screen. It seems to be cut off.
Yeah.
Okay. Sorry.
Okay, now it's good. Okay, Hudson, what do you want to ask?
Yeah, I also want to talk about the screen.
Okay, so now you can see, right?
Yeah.
So we need to include the matrices starting from A20 at the left upper part, right? The first entry, and also 3, 0, and 3, 1. If the matrices are infinite dimensional, then we believe these threes are enough, but yeah, sufficient to ensure the two moment geometry. But we also need to manually like add A441 by hand. So we need this one because A41 never appears on a diagonal line, so it is not guaranteed that A41 is positive. Yeah, this is some like a review because I personally doesn't remember these details when I look at this problem again. So for the twisted big matrix, we have to start also include like A41 minus A51, this matrix, but it's just a 1 by 1 matrix because this involves 7, and also 3, 0 minus 4, 0, 3, 1 minus 4, 1, and A20 minus 3, 0, right? We have these 4 twisted couplings, big matrices. So I just list them here. And also the polytopic constraints. Okay, enough for the details. So now maybe I can run example. So yeah, we're still calculating the Hessian matrix, but the main improvement is that I'm using a method called BFGS algorithm, which doesn't calculate the Hessian and its inverse, which is very time consuming in every iteration. So it actually finds an approximation for the Hessian by which is called B it's just determined by the previous value of B in the last iteration, like but it requires knowing the gradient only. So we can calculate using this algorithm, and it's much faster now.
Wow.
So I can obtain the maximal value in a relatively short time. So it converges, I remember, to 13.336 or 3336, something like, oh, 336.
Oh, this is
Converged it.
fast.
Yeah. Okay, so yeah, this is the optimal value found for A31. But in our paper, Liwei said that STPB without introducing a K6 null constraint, the optimal value is like 13 and 1/3. It's strictly 33333 all the way down. So there's still a gap between this and STPB.
Wei also was using spin truncation, right?
Yeah,
Yeah.
but as you said, because the null constraint involves like the null constraint 0 is between 3 and spin 4. So the relevant polytopic walls are like these two.
Yeah.
No, I mean, no, what I guess what it's asking that if you increase the spin truncation, I mean, it's approximating that value, but I mean, what is the error bar in ways result? Where
Oh, okay, I understand. You mean
I think
spin
for-
truncation actually makes it more restricted for STBB, right?
Yeah.
Oh, okay, yeah,
so
maybe.
the STP itself, also STP is not the final answer. Yeah, it itself also has a
Yeah.
given answer, a given problem. It also has an error bar.
Okay, right. Yeah, but I actually ignored this matrix, which involves only up to 6-2. So, like strictly speaking, we need this matrix. But when I add this, I don't know why, but my solver just like blows up near 13.33. So, yeah, I'm still figuring out how to fix this.
Oh, okay, cool. Sorry, is it probably because you're already hitting at the real value? Is that
Maybe, but yeah, but I put very like many conditional statements to avoid these kind of like divergence, but it still doesn't work near the optimal value. So maybe I just got something wrong.
is it just is it because of precision problems?
Yeah, I think so. But actually, I realized that after some searching on the internet, I find that actually requires some additional conditions on the step size for the iteration process.
Uh-huh.
So maybe I have to like to review these in detail, so to modify my code. Yeah.
Okay. Well, once you smooth these subtleties out, you should really write up yeah, the manual and like really the discussion of how you do things.
Oh, okay.
Yeah, I think this is a very nice doc. I mean, you should do it like you should document this.
Yeah, sure. But I think this is a well-known method, so maybe there's already some
No, but I
papers.
mean, how you know construct to solve our problem.
Oh, okay, yeah, of course. Okay. So I think the largest yeah, the main problem is that we cannot consider space that are unbounded, like including A64. I think this is the largest problem.
So basically, given if we so you're saying that the space is really a finite. I mean, in the end, you're saying that the space is a finite space because once we make up our minds where we are stopping at the null constraint, that statement tells us what are the couplings that we can consider, right? But that's basically.
So sorry, I don't quite understand.
I mean, so here we're just saying we're stopping at k equals 4 null constraint, right? Sorry, k equals 5.
Right.
Right. Once we stop there, then this tells you that you don't want to consider A64.
Oh.
And that so each null constraint defines a finite problem. That's what I'm saying. That's all I'm saying. If I'm considering
Okay,
null constraint, then I know what are the matrices that I can consider. Because
Yeah,
the unbounded ones I cannot consider. So I now have a finite set. So the number of constraint is finite.
right, right. Yeah, it's from our like algorithm's perspective, but it's just because our algorithm doesn't work for finite infinite space. It's not because our geometry doesn't include these constraints.
But isn't it that if we include these constraints, probably it'll tell us nothing new? I mean, isn't the same thing as that this constraint doesn't tell us?
What happens in the geometry? Whenever you have like some corner that's unbounded, it doesn't
Yeah.
do anything new. So you can.
Then it doesn't constrain. It doesn't help with the lower geometry that we're looking at.
Yeah, maybe. Yeah, maybe it's true.
Yeah, because I mean the result seems very close to SDP, so I think it's exactly the complete answer, right? There's no further improvement you can do. That's I think.
But I still have to add this in my program. So
Yeah, it sounds like adding that is actually getting close to SDP, even more closer to SDP result, right? You're saying that it gets you to three.
it gets very close and it blows up. So I'm not sure.
Okay, very cool. Yeah, we're gonna
think that's all.
start using. Yeah, Lorena, I think once if Fishbone gets this working, we should start to use this on the modular thing.
Yeah, I really have to like modify these to make it more reliable for the convergence criterion. And yeah. So these conditional statements are actually designed to avoid when doing iterations where when stepping forward, it sometimes goes outside the boundary, and then this actually used to prevent these things to happen. But it sometimes make the step too small so that it becomes numerically unstable and diverge. So yeah, maybe I have to think other ways to do it. Yeah, I think that's all.
Okay, cool. Okay, well, I guess we well, this project is growing bigger and bigger. Like we're really tackling all sorts of different questions. Yeah, good. So okay, maybe I also have probably my own homeworks to do. Okay, so let's just probably work and we can discuss in the middle, and maybe we can regroup probably early next week, or yeah, or if there's anything that needs to be talked about, we can regroup earlier. But
Are we going to have a meeting with Kobe group this
no,
Friday?
tomorrow no, we're not, we don't have anything set up. Yeah. Yeah, I guess Li Yuan, you're also preparing for the lecture on Wednesday, right?
Yeah, but I just I just begin like yesterday. So
No, that's okay. I think it's very laid back. Oh, we'll get to. I always heard that Kawaii-san is very. Yeah, maybe you will finally let me see his dark side.
wow, I'm prepared to be like a Beidian.
Yeah, no, I heard that Kawaii-san. I mean, the Japanese postdocs tell me that Kawaii-san is very famous for
wow.
being angry at speakers. But I said
No.
I've went to many conferences with them. I never saw that. I was wondering if it's because it's only he only does that when he's speaking Japanese. But well, okay, we'll see what's going.
Are you also inviting other like?
Yeah, a lot of the undergrads are also coming too.
Oh, okay. Like
Yeah.
how many of them?
Probably at least the undergrads that are following my discussion with them, probably 7 or 8 of them.
Oh, wow.
Yeah, so a couple of people are gonna show up, and
Okay.
yeah, but I mean it's online. So what's the difference between 7 people and 2 people? It's just like little blobs on the right, and most of them don't ask questions anyway. Yeah. Okay. Oh, did I stop? Okay, I should stop recording. Okay.